Okay, so let's work on another example together. So in this example, we are comparing two rope. In fact, we want to see that which one can we say that one of them is more elastic than the other one. We have some data points. So from these data points, we have like rope number 1 and rope number 2 for both of them. Two different types of the rope. When I say rope number 1, it's like that the rope that the type is like type number 1, and this is for the type number 2. We're gonna get two sets of the sample. So N1 is gonna be 1 is the 17, N2 is 14, X bar 1 and X bar 2. So we are gonna have the value. We're gonna find out X bar 1 and X bar 2 for it, and then we have the S1 and S2 from the data points. We can find it. So generally, we are gonna have data points. Like we're gonna have like let's say 10 data points, and from these data points for the samples, we would find out the X bar 1 and X bar 2, and S1 and S2. So we don't know the sigma, but here it says that let's assume that sigma 1 and sigma 2, they are the same. Is there evidence to support that rope number 2 is more elastic than rope number 1? So for this one, when you say is there evidence to support something, it means that we need to use the hypothesis test. We need to work with the hypothesis test for it. And for the hypothesis test, what would we do is like that, as we talked before, we have 8 steps, so we're gonna go through these steps together. Before going to the hypothesis test, like always, we want to see that which case it is. So for this one, because we don't know the sigma, we know we have S from the sample, so we would say it's like case 2. The parameter of interest is mu1 minus mu2, right? So we want to compare these ones to see that, let's say this is the some measurement that shows us that which one is how elastic is the ropes, how elastic is each of these ropes when we compare them. So what I'm going to write down here, the first thing is that I need to write down which case it is. I'm going to write down case 2. Right? So the parameter of interest is mu, and I have 2 populations. So I would write down case 2 and 2 population. So now, the next one is that it's very important that we go with this, because when we know it's case 2, it would be easier for us to know that, like quickly in your brain, you're going to think that, okay, so we're going to use t-table because it's case 2. And so the test statistic is going to be t equal to something as well. So now let's go with the steps of the hypothesis. So step number 1. Is the parameter of interest. So the parameter of interest here is the difference between these mu, right? So it's going to be which is equal to mu1 minus mu2. Step number 2 is that what's your null hypothesis? So null hypothesis here is going to be mu1 minus mu2 is equal to 0. So step number 3, I would write down okay, let me write down complete. Step number 3, it's the alternative hypothesis. For alternative hypothesis, which is, I'm going to show it by H1. In some books, by the way, they write it down HA, so that one is correct as well. So step number 3, which is H1, look at here, it says that, is there any evidence to support that rope number 2 is more elastic than rope number 1? In fact, so from here, if I say that for the null hypothesis, another way to write it down, the null hypothesis is like mu1 is equal to mu2. So for the I'm going to write down step number 3 here. So for the alternative hypothesis, we say that we want to see if we can support rope number 2 is more elastic than rope number 1. So in fact, we want to see that for the alternative hypothesis. want to see if mu1 is less than mu2 or not, right? So this is the way that when it's like this, so we say, oh, it's one-sided. We said that something is greater than another one. So this one tells us that it's one-sided. So I would write down here, it's one-sided. It's one-sided test. So in this level that we are working, we always consider the null hypothesis as equality sign, but the alternative even if it's one-sided. So one-sided, mu1 less than mu2. We want to see that if we can support this or not. And then step number 4 is that we are going to find out, we are going to write down the significance level. As I said, you can switch step 4 and 5 together. One is the statistic, the other one is the significance level. So for here, so we don't have anything, and whenever we don't have anything, we would say alpha is equal to 95%. Like we are, sorry, confidence interval is for the 95%, so alpha is equal to 5%. So here is that significance level, I would say alpha 0.05. And then for number 5, I would have my test statistic. Test statistic here is T1. So I would write down T observed. Right? And when we are looking at the equations, we see that for this one is like x bar 1 minus x bar 2 minus the delta null. So the delta null here is 0, right? Here it's 0, so this one, it's going to be 0. Divided by the, so here we are going to use the pooled estimate of the standard deviations. So it would be SP times 1 over N1, right? Plus 1 over N2. You can put this in this SP under the square root as well. You can write down like a square root of the SP power 2 times like 1 over N1 plus 1 over N2. And then for finding out SP, we would say that it's equal to the square root. So you can say SP power 2 and then you wouldn't have this square root, but now it's the same, right? So we can write down the variance or we can write down the standard deviation. So N1 minus 1 times the S1 power 2, right? Because it's under the square root, plus N2 minus 1 S2 power 2, and then we're going to divide it by the degree of freedom that we have. For this case, it's N1 plus N2 minus 2. Why minus 2? Because we are blocking like two of the, we have like S1 and S2, right? So we are blocking two data points. So here we are going to have we can find out SP, like the pooled estimate or pooled of the S. And then for the next, like step number 6, is the rejection region. So here for the rejection region, we are going to say that it's very similar to the one that we had before. If we are going to reject the null hypothesis, if T null, like T observed, is less than the minus T at the alpha, right? And then the degree of freedom that we have. So I'm going to write down here. I will continue writing down here because I want to use this area for my conclusion. So I would write down the rejection region. We're going to reject the null hypothesis if our T null is less than T, it's one-sided, so T at alpha, and the degree of freedom. So degree of freedom here is going to be whatever I have here, N1 plus N2 minus 2. So with this one, we can read the t from the table. So when we have, so look at here, so t alpha and the n1 plus n2 minus 2. So in fact, we can say here, t observed, so whatever was here, it's less than, for the t of the t at the alpha, it's going to t at the 0.05. This is 0. And then n1 plus n2, n1 is 17 plus 14 minus 2, so it's going to be 29, right? So 15, yeah, 29. So at the distance 29. For finding out this value, we can go to the t table and we can find it. So we can do that. I can show you here, or we can do that for, let's leave it for the conclusion mark. Let me just get the marker. Okay. So step number 5, 6 is the rejection region, and then 7 was the whatever calculation that we have, or computation. You can write down calculation, doesn't matter. Okay, so for the computation, what do we have? First of all is the t null. For finding out the t, or t observed, so we need to find out SP. So we are going to put down the number of the n1, n2, s1, s2, and n1 plus n2. So we are going to find out SP as the value of it is 0.1234, right? And then we just substitute that, and we're just going to put the numbers and find it. And then we're going to put it here, like I have x bar 1 and x bar 2. You're going to say 6.28 minus 6.40, and then divided by this value of the SP times the square root of the 1 over n1 plus 1 over n2. So with this, after this, we're going to find out t null. It's equal to the minus 2.51. You can go with the 4 digits as well, like 4 decimals or 2 decimals. As long as we're consistent, that will be fine. I'm going to go with the 4 decimals here. I have the number already. Okay, so we find out the t observed by putting the SP in this equation, right? So from our test statistics, the next thing that we want to calculate is that we want to see what's going to be the value of the t at the, so let's say like t at the 0.05 and 29. So for this one, we go to the table, t table. So I have the degree of freedom is 29, and then my alpha is 0.01. So I'm going to show you how to do that. Okay, so here, when we are looking at it, it's like that. This is the t table that you can see here. I just want you, it doesn't matter if you can read if the numbers are not that much clear. As long as you would see that the first column is the degree of freedom. So the degree of freedom is 29. And then here, be careful. I've seen that most of the times the students they do this mistake that, for example, when it's at the 0.05, by mistake, they're going to read it under the 0.005. Just be careful with it. Like, for example, this is 0.05, so it's going to be here, right? And then I'm going to go down and I stop at the 29. So it's going to be 1. I just read that reverse, but it's like 1.699, like here. You can do that. You can check it with your t table as well. So I will write it down here. 1.699. Step number 8 was that conclusion. We want to make the conclusion. So here, our t observed is minus 2.51, and our t for t at the alpha and the degree of freedom is 1.699. So what can we say? We can say that Oh, be careful with this. This one is 1.699 if we were looking at the positive side of it. But right now, because we are looking for the negative side of it, look at here. So it's like T null less than T alpha. So we consider the negative of this one. Just be careful with this. So it's going to be minus 1.699. So what can we say? What can we do here is like that. We would say because minus 2.51, it's a lot less than minus 1.699, right? So then we would say that it's like that when we had here. So we are working on the like this, right? It's something like this. So here I have minus 1.699 for the T at the alpha and also degree of freedom, whatever it is. So I found that minus 2.51. So minus 2.51, if I consider here as my 0, like as my center, so it's like that this length, I would go all the way down. So here is going to be minus 2.51. Okay. So as I said, you can keep it like, I didn't keep the 4 decimals because like the difference is a lot. So we are in the rejection region, right? So because of that, we reject the null hypothesis. So when we reject the null hypothesis, so we can say that, we can conclude that type, like the type 2, the rope number 2, is like it's a lot more elastic than the rope number 1. So we can conclude it because we rejected the null hypothesis. So we are with the alternative hypothesis. And this one, like the difference is a lot. So after this, we can find out the confidence interval of it. I'm going to leave it to you to find out the confidence interval. So we have the standard error here. So for confidence interval, we would just say mu1 minus mu2, right? So it's going to be mu1 minus mu2, and then you would have like your x bar 1 minus x bar 2, and then you would write down minus t at the half of the alpha, and your degree of freedom, that like minus 1.699, and then you would write down like your standard error, which is like sp times 1 square root of the 1 over n1 plus 1 over n2. So that's going to be your confidence interval. So what the final answer would be mu1 minus mu2. It's going to be greater than the it depends that if you want to work it with the one-sided confidence interval or two-sided confidence interval. So it's different. So you can do that for both of them. I would go with the one-sided because from the beginning we are talking about the one-sided confidence, like one-sided hypothesis test. Okay, so this was the example about the case 2 when we have more than one sample. So I can step aside just if you want to pause it and have everything like in front of you. Yeah, okay.